Hello children, welcome back to the channel. In my last video, we have discussed about the rotational motion of rigid bodies and we have found the equations of motion for equations of kinematics or rotational kinematics, right? The equations for angular displacement, the equation for angular velocity and the relationship between displacement angular velocity and angular acceleration as far as the angular acceleration is constant. Without discussing the reason for rotation. Now, since in case of rotation we had an angular displacement, we had an angular velocity, we had an angular acceleration. So, do we have an angular force that causes rotational motion? Because from Newton's laws of motion, we know that to cause any kind of motion, force needs to be applied. So, for translational motion, if we have force, do we have an angular force? The answer is of course no. Force is force. However, the effect of the force in case of rotational motion is measured by a new physical quantity, a different physical quantity than force itself. Now, how about a rigid body will rotate? Let's say we have a fixed axis here and a rigid body of a rigid body, right? So, if I apply certain force here at some point, say point of application of the force is here, and we apply a force like this in this direction. Let's say this is F. So what will happen? Let's say this is the case here, right? The axis is vertical here. I apply a force here, so the object will rotate. So the cause of angular movement or motion of a particle or angular acceleration of a particle is again force. However, now the force's effect cannot be measured in terms of magnitude only. Why? I'll give you a simple example. You try to open the door. So the doors are always hinged at one end, right, one side. When you push the door close to the hinge, it becomes difficult for you to open the door. But at the same time, if you go to the other edge of the door and then push it, it becomes easier. Which means if you apply the same force, say here, let's say this is our door. So if I apply a force at this point, I need more force to rotate this. However, if I apply a smaller force here, it can rotate the same by same amount. So it becomes very important to find where the force is applied. So the distance from the axis and the force, magnitude of the force, both has a role to play in the rotational effect of force. So we will define a term that will give us the rotational effect of force, and that is known as moment of force, which is another name torque. Now, what is moment of force or what is torque? Torque is a measure of the rotational effect of a force. And how it is defined? It is defined as the product of the magnitude of the force and the perpendicular distance between the axis of rotation and the line of application of the force. Now, what is the line of application of the force? See, this point is where the force is acting. This is point of application of the force. At this point the force is applied, so it is known as point of application. Now, what is the direction of the force? This. So the force will be acting along this line. So the line, extended line, in the direction of the force, this line is known as the line of application. Of the force. So the point at which the force is applied is the point of application of the force, and the direction along which the force is applied is known as the line of application. Now, by definition, torque is the product of magnitude of the force. Torque given by tau is magnitude of the force and the perpendicular distance between the axis of rotation and the line of application. How do you find the perpendicular distance between the axis of rotation, point of application of the force? By dropping a perpendicular from the axis of rotation to the line of application of the force. So let's call this as D. So tau will be force into this D. Tau, that is torque, is the product of force and the perpendicular distance between the line of application of the force and the axis of rotation. Now, what will be the dimension of torque? Clearly, it will be the product of dimension of force and of distance, which means it will be m1 L square T inverse 2. Same as work done or energy. However, it has a different unit. The unit will be, of course, force into displacement. So, unit in SI it will be Newton meter, and in CGS it will be dyne centimeter. Okay. Now, if the torque rotates the object in the counterclockwise direction, in this direction, like this, then tau is positive for counterclockwise rotation and is negative for clockwise rotation. Okay. Now, let's look at certain things. Okay, here. If I join the point of application and like this and extend this. So this will be the angle between, see, this point under the influence of force will rotate along a circular path, right? Like this. And this will give us the radius vector for the circular path. Right? So if I take this as r vector, then this angle theta will be the angle between the radius vector and the force vector. Okay. Now if I look at these 3 points, let's call this O, this is point of application, so P, and this is say L. So delta OLP, if we look at this particular triangle, what do we get? Okay, so what we see in this delta OLP is that this is the perpendicular and this is the hypotenuse, and this angle must be equal to theta. So using trigonometry we can say that D by R equal to sin theta, or D equal to R sin theta. So we can rewrite this as F into R sin theta. Okay. Now if I write this as F into R sin theta, then we can say that this equals to modulus of R cross F we can also say it's modulus of F cross R, but if we say it's F cross R, F to R, this is R cross F, right? R to F it will be here, and F to R it will be into the board or into the negative direction of the axis, x-axis. But we have already said that torque is, if we has to move it this way, then torque has to be positive. For torque to positive, it has to come out of the board. Tau has to come out. So if you look at R cross F, R to F by right hand thumb rule, the torque vector will be positive direction. If I say F to R, torque vector has to go negative direction. That is why this has to be positive, R cross F only. So modulus of tau is this. So in vector form, we can say that tau will be equal to R cross F. Are we clear till now? So moment of force or torque, which is given by force into perpendicular distance between the axis and the line of action of the force, is nothing but the cross product of R radius vector, that is the vector from O to the point of application, and then the force vector. So that is why if we take are smaller, that is point of application is smaller, so closer to the hinge, as we have discussed in this case. When R is smaller means this distance will be smaller. So if I apply force closer to the hinge, it becomes difficult for me to rotate it. But when R increases, the magnitude of R cross F will increase, and that's why the same force will be, it will be easier for us to open the or move the door or the book about a given hinge or given axis of rotation. That is why torque is not constant for the same magnitude of force or for same magnitude and direction of force. If the point of application is closer to the axis, the effect of the rotational effect of the force will be lesser, and hence the torque will be lesser. As we move further and further, the rotational effect will increase. Okay, we have just seen that torque due to a force applied at a point P on a rigid body. I haven't drawn a rigid body now for the clarity of the picture, which is rotating about an axis, the y-axis, is given by tau equal to R cross F, where R is the vector, position vector of the point of application of the force. Okay, or in magnitude, tau equal to F into D, where D is the perpendicular distance between axis of rotation and the point of or line of application of the force, and which can be given by F or sin theta. Now, what we can do is that we can rewrite this as R into F sin theta, right? So, if we resolve this vector, force vector, into two components, one along the radius vector and one perpendicular to the radius vector. So, perpendicular to the radius vector means it will be along the tangent to the circular path of the particle that will be moving in this circular path. Okay, so if I resolve the force vector, then this radial component will be F cos theta, and the tangential component, let's call this F theta, P equal to F sin theta, right? So what we can say is that tau, which is equal to R F sin theta, is equal to R into F theta, right? What it means? It means that out of the net force F that is being applied at the point of application P, only the tangential component of the force, which is F sin theta, F theta equal to F sin theta, the tangential component. Only the tangential component will contribute to the torque. The radial component, being along the radius vector and perpendicular to the direction of motion, will not contribute anyway to the torque. Okay, clear? So now if we move on to the vector equation, tau equals to vector tau, torque vector equals to R cross F. So we can write in terms of rectangular components that tau x I cap plus tau y j cap plus tau z k cap, which will be the tau vector or the torque vector, must be equal to x I cap plus y j cap plus z k cap cross force vector f x I cap plus f y j cap plus f j k cap. We know how to expand this right hand side, right? What we'll do, we'll do the determinant form I, j, k, x, y, z, and fx, fy, fj, and then open the determinant to find the components. So the components will be I with I, it will be y fz minus j fy, plus with j it will be z fx minus x fz, and with k cap cap, okay, it will be ijk cap, it will be x fy minus y fx. So if we compare all these two sides, this vector and this vector must be equal. So their respective components, that is x component, y component and z component, should be equal, which means tau x can be given as y fz minus z f y. Tau y will be given by z fx minus x fz, and tau z will be given by x fy minus y fx. Okay, alright. Now let us consider we have a rigid body here which is free to move above this particular point on top of a fulcrum. Now let us say there is a torque here which is trying to rotate this in the counterclockwise direction on the left hand side. Let's call this tau 1. And another torque here, tau 2, which tends to rotate it in the clockwise direction. So the rigid body to be in rotational equilibrium, that is, the rigid body, if it was stationary, it should not start rotating. Then these two torques must be equal, right? Tau 1 must be equal to tau 2 in magnitudes, and they should be opposite. Of course, they are opposite, as we have shown. So for the object to be kept in equilibrium position without rotating, we have to have both the torques equal to each other. Now, how do we produce torque? By applying certain force. So what we do here is that we apply a force, right, with the help of certain weight, and we apply another force with the help of some other weight on either side of it. Let's say this force's point of application is at a distance of d1 and the other force is at a distance of d2 from the fulcrum. And let's say this force is F1 and this force is F2, which is nothing but the weight of the two objects. And so we can simply say this is equal to m1 into g and this is equal to m2 into g. Okay. So principle of moments, which says that for the object to remain at rotational equilibrium, the torques in the counterclockwise that is trying to rotate it in the counterclockwise direction must be equal to the torque that is trying to rotate it in the clockwise direction. This will mean that since this force is vertically downward and this is horizontal, so the perpendicular distance between the line of application of the force and the fulcrum point of rotation for the left hand side will be, force will be F1 and distance will be d1, and this will be F2 d2. So this particular expression tau 1 equal to tau 2 or F1 d1 equal to F2 d2 is known as the principle of moments. Now this simply means from our, this is W1, from our diagram it means that W1 weight of the first object multiplied by d1 must be equal to W2 weight of the second object multiplied by d2, where d1 and d2 are the perpendicular distances from the point of application of the weights from the fulcrum or from the point of rotation, axis of rotation. Axis of rotation will be in the perpendicular to the board. Okay. So weight can be renamed as load, and this length is named as load arm. So if we have a lever, then whatever load we put here will produce a torque, and that torque will be dependent on the weight or the load and the distance, perpendicular distance of the point of application of the load from the point of rotation. This is known as load arm. Then on the other side, what we need to do is that we have to apply certain amount of effort. At the end of the arm where we apply the effort, that arm is known as effort arm. So W1 is the load, D1 is the load arm, W2 is the effort, and D2 is the effort arm. So load into load arm equal to effort into effort arm. This statement is what governs a lever, and that is why functioning of a lever, and that is why this statement is known as the principle of lever. So principle of moments says that for rotational equilibrium, the torque should balance each other. The torques trying to rotate it in one direction must be equal to the torque trying to rotate the object in the opposite direction. And principle of lever says that, which is a derivative of the principle of moments, we will say that load into load arm equal to effort into effort arm. Both are basically the same statement. Alright, now let us say we have a rigid body, and on this rigid body, which is moving around point O. The axis of rotation passes through point O and it is perpendicular to the plane of the board. Now let us say we apply a force equal to F to A, point A, and we apply an equal force of equal magnitude but opposite direction, that is to say minus F in the other arm. Okay, so we are considering only the magnitude of the force. So what we are doing is that we are applying two equal and opposite force at two different points on either side of the axis of rotation. Such a couple of forces, such two forces which are equal in magnitude, opposite in direction, and their points of application are different. Such forces are known as a couple of forces. So a couple of forces, two equal and opposite forces having different lines of action or line of application, as we have seen here. So in that case, what will be the torque produced? Now let's consider point A, point of application A. Here what will happen, because of the force, the object is going to rotate in this direction. And we have chosen for our convenience that the force is perpendicular to the line OA, which means tau1 torque for the first force will be F into AO, force into perpendicular distance. Similarly, for the second force, F applied at point B, it wants to rotate it in this direction. So magnitudes, in magnitudes, not in vector relay. Also vector relay it will be true, but we are taking magnitude. So this will also be F into OB. Right. Now what we are seeing is that F1, the first force at A tries to rotate it in the anti-clockwise direction. Force at point B also tries to rotate the object in counterclockwise direction only, which means that both the forces will add up, or both the torques act in the same direction. So both the torques will add up, which means the net torque of the couple will be tau1 plus tau2, which will be equal to F into AO plus OB, which is equal to F into AB. If I call this distance between the 2 points D, then this will be equal to F into D. So tau will be the moment of a couple. This is moment of the first force, this is moment of the second force. Their sum is the moment of the couple, both the forces. So moment of a couple is equal to force into the distance between the points of application. Point of application, right? Which means that moment of a couple will be independent of the choice of the axis of rotation. Why? See, whether I choose point O here or I choose another point here, O dash, even if we have to rotate the apply the forces at point A and B, what will be the moment of the couple? In that case, it will be tau equal to tau 1 dash plus tau 2 dash, which will be equal to F A O dash plus F O dash B. The sum will still be A B, which is F into D. So whatever be the choice of axis is immaterial for the moment of a couple, or that is the turning effect of a couple, right? Okay, now let us say that a rigid body is rotating under the influence of a force whose magnitude is given by F. Okay, F is the magnitude of the force. So let us say in a very small time, under the influence of the force, the object rotates through an angle of delta theta. The angular displacement is delta theta. So in rotating the object from initial position and moving it from P to Q, in traversing this arc length of PQ, some amount of work has been done. We want to find what is the work done by the torque. So what will be the small amount of work done when it moves through angle delta theta? That will be equal to force which is tangential. Since P and Q are very close to each other, the displacement and the force's direction can be taken to be the same, and that is why we can say that this will be equal to force into the arc length of PQ. Okay, the distance of the point P from O is R and the radius vector is R vector, right? So magnitude is R. So this will be equal to F into R delta theta. Why? Because we know that the angle subtended at the center is given by arc length divided by the radius vector. We know that. That's why we have written this. Now if we consider the time to be very, very small, delta t tends to 0 implies delta theta will also tend to 0. So in the limit delta t tending to 0, these delta terms can be written as d. So we can say in the limit delta t tends to 0, dw equal to f r d theta. Or we can say dw equal to tau d theta. For circular motion of the path, since f is approximately tangential to it, so we have to say that f is applied tangential, and so r cross f will be equal to f into r sine 90 degree, and so we have fr equal to tau. Okay, so if it is so, then the net work done will be given by W equal to, we integrate it from the initial position, say the object was at theta 1 when we started the measurement and it ended up at theta 2. Then this expression will give us the total work done in rotating the object from initial position of theta 1 to final position of angular position of theta 2. Okay. Also, from this expression, dw equal to tau d theta. If we differentiate both sides with respect to time, what we get? dw by dt, tau, force into the radius vector which is independent of time, so tau will be outside and this will be d theta by dt. But dw by dt gives us instantaneous power or power, right? So power will be equal to tau, d theta by dt is omega. So these two also are very important. dw is tau d theta and power is given by tau into omega. Okay. So in our next video, what we will do is that we will move on to a very, very important topic, and that is known as angular momentum. Angular momentum and its conservation is one of the very important laws of physics which finds its application in many different fields of physics. So I would suggest you pay utmost attention when we discuss that particular topic in the next video. Okay? Thank you.